The unit may be stated with the prefix that represents a power of 10 multiple or submultiple. Complete table 1.1 to show the name and symbol of each prefix and the corresponding power of 10 multiple or submultiple. Kilo is 10 power 3, mega is 10 power 6, tera is 10 power 9, kilo mega tera. And over here, know that micro 10 power negative 6, nano is 10 power negative 9, and pico or pico 10 power negative 2. Sorry. Giga is 10 power 9, and tera is 10 power 12. So in the following list, underline all the units that are SI based units. So meter is an SI based unit and ampere is an SI based unit only. The potential difference V between the two ends of a uniform metal wire is given by V is equal to 4 density into length into current over pi d squared. D is the diameter. For a particular wire, the percentage uncertainties in the values of some of the above quantities are listed in table 1.2. The quantities listed in table 1.2 have values that are used to calculate density as 4.1 into 10 power negative 7. For this value of P, calculate the percentage uncertainty. Okay, so from this equation, we need to make rho the it's actually resistivity subject. So what we'll do is resistivity is equal to voltage into pi d square divided by 4 Li. Now we just like put in the percentage uncertainties. Resistivity for voltage has a percentage uncertainty of 3.5. Pi is a constant, so we will not consider that. And voltage percentage uncertainties, if the two values are being multiplied or divided, then the percentage uncertainties they add. So 3.5 plus, and if the term is being has a power, then it's the percentage uncertainty is multiplied with that power. So if it's t square, then that means it's going to be 2.0 plus 4 is again constant. The profile is 2.5 and percentage uncertainty of I is 2. Zero. So the percentage uncertainty of rho you get is 14%. The absolute uncertainty. Basically, the absolute uncertainty over the measured value is basically the percentage uncertainty. So if we multiply the percentage uncertainty by the value, we should essentially get the absolute uncertainty. So the absolute uncertainty over here is 6.6 into 10 power negative 8 ohm meter. Question number 2. A charged oil drop is in a vacuum between two horizontal metal plates. A uniform electric field is produced between the plates by applying a potential difference of 1340 volts across them. Okay, as shown in figure 2.1. So basically, this is the charge aura. Okay, wait. This question is about electric fields, so just going to skip it since it's not in the new syllabus. Define power. You know that power is basically the work done over time. So we can just write power as work done time. You can derive definitions from their formulas. A car of mass 1700 kg moves in a straight line along a slope that is at an angle theta to the horizontal, as shown in figure 3.1. Car moves at constant velocity for a distance of 25 meters from point A to point B. Air resistance and friction provide a total resistive force of 440 Newton that forces the motion of the car. So basically, this friction force is 440. State the change in the kinetic energy. If the car is moving at constant velocity, then basically change in kinetic energy is basically uh, 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 final kinetic energy minus initial kinetic energy, right? So if both are the same, so there will be no change. So it will be 0 joules. Calculate the work done against the total resistive force. So you know that it has a resistive force is 440, and work done is basically force into distance moved. So it will be 440 into 25. Distance moved will be equal to 1.1 into 10 power 4 joules. The movement of the car in B from A to B causes its gravitational potential energy to increase by 4.8 into 10 to the power 4 joules. Calculate the increase in vertical height of the car for its movement from A to B. Okay, so we have the mass of the car, and we know its change in potential energy. So we know that uh, increase in gravitational potential energy is basically equal to mass into gravity into height. This is the weight into height, same concept as work done into distance. So if this is 4.8 into 10 power 4 joules, mass is 1700 to 9.81 to h. From here the h we get is 2.9 meter. Now they were asking for the angle theta. That's pretty easy. We have calculated h, like this height, so we know that sine theta is going to be equal to h over 25, perpendicular over hypotenuse. So theta is going to be sine inverse h, which is 2.9, and the hypotenuse, which is 25, and hence we get 6.7 degrees. The engine of the car in part B produces an output power of 1.7 into 10 power 4 watts to move the car along the slope. Calculate the time taken for the car to move from A to B. So we know that power is basically equal to work done over time, right? And um, the work done by the for, for the force of the car is also equal to 440 since it going at constant velocity, right? So the resistive force is going to be equal to the forward direction force. So and the distance we also have that. So work done we figured out was 440 into 25. And to find t, just divide it by power, which is 1.7 10 power 4. Um, so this was the work done against resistive forces, and there was also work been done against the force of gravity. So we will also have to consider that as well, which is going to be 4.8 10 power 4. So basically, time will be equal to 3.5 seconds. We can apply the same concept from mathematics mechanics, which is change in energy to change in work done. This is, I think, easier. Since change in energy, we have gain in potential energy, which is magnitude 4.8 to 10 power 4, and we have zero change in kinetic energy. And then basically the work done by the car, it's x, which we have figured out, minus the work done against resistive forces, which is 1.1 to 10 power 4. So work done by the force of the car is basically 4.8 and 10 power 4 plus 1.1 10 power, which is equal to this, and which gives us 3.5 seconds. Yeah. A child sits on the ground next to a remote controlled toy car. At time t is equal to 0, the car begins to move in a straight line directly away from the child. The variation with time t of the velocity of the car along this line is shown in figure 4.1. Basically, we can say that this is the child. Apologies for my drawings. And this is the car. So for the first 2 seconds, its velocity increases, then it's constant for another 2 seconds, and it decreases. The car's horns continually emit sounds of frequency 925 Hz between times equal to 0, time t is equal to 6 seconds. Speed of the sound in air is 338 meters per second. Describe qualitatively the variation, if any, in the frequency of the sound heard by the child that was emitted from the car horn. Okay, so we know that the observed frequency is equal to frequency of the source multiplied by speed of sound divided by speed of sound minus the velocity of the source, or plus minus. Since it's going away, then we'll consider minus. So these are like tricky questions. So they've asked us to describe qualitatively the variation in the frequency of the sound heard. So we know that initially it's zero velocity, so it's going to be the same frequency of the horn that the child is going to hear. But as time goes, it increases to the velocity is increasing. So if the velocity is increasing, that means that uh, uh, it means that sorry, the the system is going away, right? So it's going to be plus. So the initial velocity of the car is increasing. So the whole, like, this term is going to increase. So and since this term is constant, then FO we get is directly, and this is also constant. So we can say that FO is inversely proportional to the speed of the car. So if the speed of the car is increasing from t is equal to 0, then the observed frequency will be decreasing. So observed frequency decreases. From time t is equal to 4 seconds to t is equal to 6 seconds. Again, Now, the velocity of it's the same relation because the car is still going away, but with decreasing acceleration. So the this deceleration, sorry. So the speed of the car is decreasing. That means that the observed frequency will increase. In these type of questions, you basically need to like figure out the relationship of the two variables, like frequency of the sound heard from the frequency. So we need to figure out frequency. So and we know the only change that is happening is in the velocity of the car. So that's what you need to do in like similar types of questions. Observe frequency basically increases. Determine the frequency to three significant figures of the sound heard by the child that was emitted from the car horn at time t is equal to 3 seconds. So we'll basically use the same formula, frequency of source into speed of sound, plus or minus speed of source. Speed of frequency, the source is 925 hertz. Speed of sound is 338 with 338 plus at time t is equal to 3 seconds, the velocity of the car is it's 12 meters per second. So the f observed frequency which you get is 893 hertz. Okay. Well, determine the time taken for the sound emitted at time t is equal to 4 seconds to travel to the child. Okay. So to find time, the, let's say the car is at time t is equal to 4 seconds, the car has traveled to this point. Okay. Uh, Determine the time taken for the sound emitted at time t is equal to 4 seconds to travel to the child. So basically, over here, you, you just use a simple formula of distance over time. Sorry, distance, speed is equal to distance over time. Find the time taken for the uh, wave of the sound wave travel to the child. So at 4 seconds, let's assume the car is over here at this position and it's traveling in this direction. So we need to calculate this distance. So, and we have the speed. So if we can calculate this distance, then we can easily find the time taken. So we know that distance in the they have given us the velocity time graph of the car, and we know that the distance or displacement is the area under the graph of the velocity time graph. So if you can see, then we need to calculate this distance right here. You can add the area of the triangle and the square separately, or think more quick, faster way will be to like add the area of the trapezium itself, which will be half into the sum of the parallel sides, which is 2 plus 4, into height, which is basically 12. And you know that speed is equal to distance over time. So time is equal to distance over speed. So we just divide this by the speed, which is 338 meters per second. and hence we calculate this. We had 0.1065, which is approximately 0.11 meters per second. Since they've given us the values in two significant figures, mostly, like the minimum for the time they've taken two significant figures, so that's what we're going to do. Two significant figures for this question. It says the waves, uh, stationary waves question. The tube is initially fully submerged in water. The axis of the tube is kept vertical as the tube is slowly raised out of the water. Okay, so this is basically the experiment to find the speed of sound. It's a specific experiment which is in our syllabus, and it's a very simple experiment. A loudspeaker producing sound of frequency 530 Hz is positioned at the open end of the tube and it is raised. The water surface inside the tube is always level with this water surface outside the tube. Speed of the sound in the air column in the tube. Speed of sound in the air column in the tube is 340 meters per second. Describe a simple way that a student, without requiring any additional equipment, can detect when a stationary wave is formed in the air column as the tube is being raised. Okay. So, uh, you know that when stationary wave forms, like at the source, there's also always an antinode. Let's say this is a node. So this what stationary wave might look like. So when a stationary wave forms, then the sound, since like the amplitudes of the sound waves, which is sound wave which is coming from here is reflected at this from the surface of the water, and their amplitudes they align to superimpose interfere to form a stationary wave. So basically the displacements are added, right? So the amplitude of the sound loudness of the sound will be like increased, so a louder sound will be heard. Okay. Determine the height of the top end of the tube of the surface of the water when a stationary wave is first produced in the test tube. Assume that an antinode is formed level in the top of the tube. Basically, there are no end corrections. So the antinode is being formed over here, and in a wave, uh, we have the first node, and then we have the antinode. So this is what the stationary wave is going to look like. Going to look like somewhere like this, like we did. And when it is in second period, it's going to look something like this. It's basically 1/4 of the wavelength of the whole wave. That's the first which can form. Wait, no, it's going to be somewhere something like this. The node is going to be over here. That's what it's going to look like one node and one antinode. Yep, that's more suitable. Determine the height of the top of the tubes over the surface of the water. So we know that V is equal to F lambda, and we have the frequency of the sound wave and the frequency. So we can calculate the lambda, which is going to be 340 over 530 is 0.64 meter. And you can see that the stationary wave being formed is like it's just a quarter of the whole wave. So this is one stationary wave, and the which is the wave which is being formed is only like a quarter of the whole stationary wave. So we can say that if this is one lambda, then this part right here is lambda over 4. So uh, h, the height is equal to lambda over 4, since this is what essentially we're trying to find. So we can say 164 over 4, which gives us 0.16 meters. That's the height of the speaker. Okay. They've asked us to this the wave question, stationary wave. Determine the distance moved by the tube between the positions at which the first and second stationary waves are formed. So basically, um, we know that there are always an antinode to the source, and there's a node at the reflection point. The first wave, stationary wave, will look like this, right? This and this. But in the second stationary wave, you know that it starts like this. So antinode and then the other antinode and other node. So it's going to look like this. So we have another node, this. That's what it's going to look like. So first it was at over here, then it moved like almost half a wavelength. So the distance, the wavelength was 0.64. So half a wavelength was going to be 0.32. Okay, Olivia. A cell of electromotive force 0.48 volts is connected to a metal wire X as shown in figure 6.1. The cell has internal resistance. Current in the cell is 0.8 amperes. Wire X has length 3 meter, cross-sectional area this, and resistance this. Calculate charge passing through the cell in a time of 7.5 minutes. So we know that the current is equal to charge flowing in per unit time. Charge is basically going to be current equal to time 7.5 to 60, which is equal to 360 volts. Calculate the percentage efficiency with which the cell supplies power to wire X. Okay, so you know that the cell is producing a voltage of 0.48 volts. So you know that the power of this cell will be equal to, first we calculate the power of the cell, then we calculate the power uh, of the wire. Power of the cell is equal to 0.48 Pi. We, we have multiple formulas for power, Vi, or we can also use P is equal to V square over R, or P is equal to A square R. Similar formulas. 4 into 0.8. That's the power of the cell. We call it P cell. That is 0.384. Now the power which is emitted by wire X is basically 0.8 is I square into R 0.4, that is 0.256. So the efficiency will be 0.256 if I was 0.384 into 100, which gives us 67% approximately. There are 3.2 into 10 power 22 free conduction electrons contained in the volume of wire X. For wire X, calculate the number density N of the free electrons. Basically, number density is equal to the number of electrons divided by the volume. Now, you know that they've given us the cross section and they've given us the length. So from there, we can calculate the volume. Let's take the wire as a cylinder. They've given us this area cross section and they've given us the height or length. So from here, we can calculate the area. It's going to be 3 into cross sectional area 1.3 into 10 power negative 7. This gives us 8.2 into 10 power 28. 20. Average, now they've asked us to calculate the average speed of the electrons. So over we just use the formula for current, which we need to memorize. N is equal to NAV, where N is the number density, I is the current, A is the cross-sectional area, V is drift velocity or drift speed, and E is the elementary charge, of which the value is given to us in the formula sheet of paper. The elementary charge is equal to this 1.6 upon negative 19. So we need to calculate P. So just make P the subject. I is equal to NAE. Current is 0.8. And we calculated is 8.2 to 10 power 28. And area is 1.3, 10 power negative 7. And the elementary charge, which you just saw right now, 1.6 into 10 power negative 19. The average just speed of velocity which we get is equal to 4.7 into 10 power negative 4. The wire Y has the same cross-sectional area as wire X and is made of the same metal. So it's basically have the same resistivity. Wire Y is longer than wire X. Wire X in the okay, wire X in the circuit is now replaced by wire Y. Assume that wire Y has the same temperature as wire X. State and explain whether the average drift speed of the free electrons in wire Y is greater than the speed as greater than, the same as, or less than that in wire X. So in these type of questions, you just need to figure out the relationship of different variables in the question. So we calculated that the drift speed is equal to current over drift charge density over area over electron. So basically, the current is the same since it's the same battery, but that the resistivity is equal to resistance equal to resistivity over L length over cross section area. So if they're made of the same metal, that means this is constant. Same area, this is constant, but since y is longer, then that means length is more. So that means the resistance of the wire will also be more. And since we know that V is equal to IR, so the and V is constant. So if the resistance increases, then the current decreases since I is inversely proportional to resistance. So if the resistance is increasing, then uh, then the current will decrease. So if the current is decreasing, charge density it's the same since it's the same metal. Cross section area is also the same. Elementary charge is also always the same. So the drift velocity will actually decrease. Now just explain what we just proved right over here. Since resistance increases, So current decreases. Okay. So now, a stationary nucleus peak of mass 243 atomic mass units decays by emitting an alpha particle, mass 4 units, atomic mass units to form a different nucleus Q, as illustrated in figure 7.1. The initial speed of the alpha particle is 1.6 in 10 power 7. Use the principle of conservation of momentum to explain why the initial velocities of nucleus Q and the alpha particle must be in opposite direction. So basically, the principle of conservation momentum is that the total initial momentum is equal to the total final momentum. Now, if you see carefully over here, you can see that the before decay, nucleus P is stationary. That means it has a velocity of zero. So if it has zero velocity, that means that momentum, which is equals to mass into velocity, is also zero for P. So, and we just proved said that the final momentum should be equal to the initial momentum. That means that the momentum over the sum of the momentums of these two particles should be equal to zero. And that is only possible if this has a negative value, if this momentum is negative, since it has a mass here for you and it has a positive velocity, then this means this is positive. So this is and the mass cannot be negative. So its speed velocity is what's going to be negative. And that's why they both are supposed to move in opposite directions. Right, that total momentum for decay is zero. So total momentum after decay should be zero. And alpha particle and Q have momentum in opposite direction. Tap the initial speed v of nucleus Q. So just use the formula of conservation of momentum m1 u1 plus m2 u2. Sum of the initial total momentum is equal to final total momentum m1 v1 plus m2 v2. So you know that the total initial momentum is zero. The final momentum, let's take m1 as the alpha particle. It is 4u and into 1.6 into power 7 plus m2. Since the station nucleus had a mass of 243 atomic mass units and it emits an alpha particle, so that means that its mass is now reduced to the new nucleus which formed in Q will have a mass of 243 minus 4, which is basically 239. 39 V. And from this equation, V we can calculate as, and since it since this is a V as well, U as well, so when this term goes over there, the U's cancel out. You can take U common out here and divide by 0, you get a 0. So V we get is 2.7 to 10 power 5 meter per second. Calculate the initial kinetic energy in the alpha particle. Okay. So basically, this MEV I think is not in this syllabus anymore of 2025. So just calculate the initial kinetic energy, which is going to be half to mass, which is 4U, and U is basically 1.66 into 10 power negative 27 kg into velocity squared. So the kinetic energy which we get 8.5 into 10 power negative 20. The graph of number of neutrons n against proton number z is shown. The graph shows a cross that represents nucleus P. Okay, so we check then 95 and 48 should add up to 43. Yes. A nucleus R has a nucleon number of 242 and is an isotope of nucleus P. That means it has the same proton number and different neutron number. Nucleus R decays by, so that's possible only possible when it has one less neutron, emitting an electron, beta negative with an electron to form a different nucleus as on figure 7.2 draw across to represent the nucleus R, the nucleus S. Basically, R has 95 protons, but it has one less neutron, so that's what R is going to be. And it emitted a beta negative particle, so that happens when a neutron it converts into a proton, and this is what causes the production of the beta negative particle and an antineutrino. So if it's another neutron converted into a proton, that means its neutron number decreases and proton number increases. So that's where S is going to be. State the name of the other lepton in addition to the beta negative particle that is emitted during the decay of nucleus R. We just wrote that previously, which is an antineutrino. This you have to just memorize this equation. Okay. Hopefully, this paper was not very difficult. It is an old paper, so there are some questions which are not in the new syllabus. But other than that, should be pretty easy to do. Hopefully, inshallah. Yeah, I feel that this question might have been explained a bit better. So